So welcome back. I put up this slide that we had seen earlier. So what we've done so far was the RSF, where what we want to model is the range distribution. So where do we find the animal in the landscape? So what proportion of time is it here or there? And what we now want to do is exploiting more of this movement character that in the data, because here we essentially in the model we just took the points, and there was not the movement structure there was not extra exploited. We only exploited it to calculate what is the degree of independence of a given point. Now we want to come up with a model that actually simulates movement over time. Yeah? So instead of saying where in the landscape am I going to find the animal on average, how much time is it there, we are now going to look at what's the probability that given I'm here right now, where will it be in, say, 3 hours? And then once we know that, we can move the animal there and then ask again, where will it be in 3 hours, and so on and so forth. So what is nice here is we are going to have something that is giving us a trajectory. The drawback is we are having something that is discrete in time, and Eli talked a lot about this, and Chris and Dinesh, why there's a big interest in doing things in continuous time. So there are certain things that we can't do here, but it is now a tool I'd suggest that is nice because it's easy to use, and that it allows us to say something about how the positions in the landscape over time where the animal is found change. So this is just more explicitly what the SSF does. It predicts the probability of the animal's next position based on its current position, and potentially also the direction of movement, and then the environmental conditions in the landscape. So in terms of memory, this system has at best the memory of where I came from, but that's it. So it is a Markov process. We had that also. I think Eli introduced this. So our model doesn't have a memory of what the animal did yesterday or 2 days ago. It's just now that I'm here, potentially now that I'm here coming from there, where will I be next? Okay. So on the left, the realized trajectory on the DEM, and to the right, the model probability of where the animal would be 3 hours after that it had been at the point marked with a cross. So movement here is discrete in time, and in general, we assume that it's a single fixed time step. There are two recent papers that came out this year where there were methods or ways suggested how we can go around that a bit. So if a step is missing, so if you have a gap of, say, 3 hours or more, there are some ways of dealing with this, but still the basic assumption of this method is we have a single fixed time scale. And we assume that once I've made a step, the next step is not dependent on what happened before. So the technical term is here, we assume that there's no autocorrelation in the velocities. This does not necessarily imply that the animal is making a completely new decision where to move next at this time scale of 4 hours. I'll show you an example of how you can also analyze and simulate movement during a migration. So there can be something that affects the movement in the long term. Yeah? You can have that. But just from the point of view of the statistics, or point of view of the likelihood, we assume that these individual steps, each step provides a completely new information. And so we don't have to downweight these the steps. Yeah? That's what's happening. Yes. Where's the thing?
You're saying that there's no correlation in velocities.
Yes.
So that is implying distance between points. But what about angles? Would also that be affected by, like, it needs to also have an independence on the
velocity here has two elements in it, sort of the distance covered in that, say, time, and the directionality. So we, in principle, also make the assumption that there's no correlation in the angles. We allow, in the model, often we allow that there is a tendency to move in the same direction from the last step. But once we've taken that into account, there is this step is supposed to be completely so sort of what happened 2 steps back, for example, doesn't count anymore. So we allow for this tendency to walk in the same direction as the last step.
Okay.
So now, how does this form? How do we quantify this probability of being at a certain point? So this is, when you look at this equation, it is very similar to what we've seen before. This is the probability that the animal is at this location, and now we have time here at time t plus delta t. So in 3 hours. Yeah, delta t is our time duration that we're looking at. I always use 3 hours because Scylla will use 3 hours. Yeah? Your animals will probably have different time steps. So where is this animal going to be in 3 hours? Well, we expect it to be that a function of the habitat, so the h there, of where the animal could be in 3 hours. So if this is here our trajectory, it was here, then moved there, and then there. So the idea is the probability of being there in 3 hours depends on the environmental conditions at that point. Okay? And then there's another part there that's a bit wild, and that is what we call the movement kernel. So this is something that should depend on how far that point is from where I'm now, and potentially what's the angle of this movement direction relative to where I came from. So this angle here. And when the animal came from here, and now this point has a certain probability of being chosen, not only because there are certain resources there, but because it is at a certain distance and at a certain angle from where I'm now and from where I came. Yeah? So you could also think of this as, where would you expect the animals to be in 3 hours if you had no information about the environment? And if the animal didn't care about the environment, if it was homogeneous, still the animal would probably be rather close by to where it is now, and would make a certain step of a certain length. Yeah? So this is this thing phi there is what we call is the movement kernel, the selection-free movement kernel. Yeah, so that is a bit described by the distribution of step length and turning angles. And then the same happens, that always happens because we want to have a probability there. We take what we have there in the nominator, we stick it down here, and we make an integral over the whole area. So that ensures that the thing to the left is a probability density so that it nicely integrates to 1. This similar structure to what we had earlier. Earlier we had the selection there, and then we had here this home ranging term. Yeah, but instead of a home ranging term, we now have something that describes the movement at this time scale of delta t. So, for example, at the time scale of 3 hours. And I took this illustration here because this is how this was often represented, the step selection functions. You have a realized step, say from 2 to 3, and you compare it to alternative steps. Yeah, so this is use versus availability. So you compare the use step versus available steps. And what this formula there suggests is that we shouldn't have just here 5 or 6 points in the landscape, because we want to represent all possible steps that the animal could have taken from here. So we have to integrate over the whole landscape. Yeah. And earlier we did this by integrating over the whole. We calculated the probability that the animal was at a given point for the whole landscape and divided by that. And that was cool because we had only one landscape to deal with, sort of one, to do this integral once because it was the same integral for all points. Now here, each time we move, we have to calculate a new integral because our movement kernel will be different at each point. So once I'm here, this point will be closer than it was when I was here. Yeah. So I have to calculate, I have to do this integral for each point again and again and again. So that is why typically we don't integrate over the whole landscape each time, because that would be very numerically expensive. So if you have 1,000 steps, it would be 1,000 times as expensive as in an RSF. So what we do is we take alternative steps that it could have taken, but instead of taking 5 or so, we take, I would suggest, at least 200. Yeah, or even more.
So for those 200 alternative steps, is the distance of those constrained?
The short answer is no. In practice, it'll be constrained. What we typically do is we first look at the step length distribution for that animal, and we fit a distribution to it, a gamma distribution typically, because that is convenient for the analysis. And then we draw our alternative or potential steps from this gamma distribution. So in practice, there won't be infinite, but the gamma distribution doesn't have an upper limit, so it could be very far.
So it's constrained biologically
Yeah.
to like biologically realistic values for the step length
Yes,
for that species or for that animal.
So the idea is that, yes, we have to integrate, but this point here will anyway have a probability of 0 that the animal is there. So we don't have to take this into account in our integral, because that point will have a probability of 0 anyway. So, I mean, I think of integrals always as a sum over discrete entities. So I always think of this as I have a raster layer, and I have now, in theory, to calculate for each pixel in the raster layer a value. That's this value here. And then I have to sum them all up. And the idea is that apart from this area here, everything is anyway 0. So I don't have to calculate these things here. But here, around where I'm currently, the probabilities will change a lot. So that's why we put in a lot of sort of background or integration points, or the technical term is quadrature points. We put them here. And so we draw them from a distribution that corresponds to what the animal is doing in practice. Yeah. We'll come back to this later. But what we can remember now is to calculate the integral, we throw in a large number of randomly chosen points, calculate the relative weight, our lambda, going back to the very first slides, our lambda at that point, and then we sum them up. And that's our approach for the integration. I have one particular slide for this at the very end to talk a bit more about the details, but this is the rough idea. Yeah. So now that we have this part, we want to know how do we calculate here the selection, which is our function w, which is and there we do the same thing as earlier. So this is our w. This is the selection function. We had it earlier for the elevation, that this was a quadratic function. So it was using elevation and elevation squared. And here we do the same thing. It's exponential to make sure that the values are larger or equal to 0. And then we multiply the habitat value at the location of the next position, either the realized next position or one of our 200 alternative steps. We extract the habitat value there and multiply it with our coefficient that tells us whether this habitat, this resource is preferred or avoided. And then we take the sum over, here the sum is over all different raster layers again. So the I here are the different raster layers. So this is essentially the same thing as before, but now we take the position in, say, 3 hours, the realized one, and the potential ones. So this is the selection that we had before. And then we have this part that is the movement kernel. This corresponds to what we had earlier with this home range, where we were using the distance to a home range center. And here we now say, well, this is the distance to where I'm now. This is the step length. That's the distance to where I'm now. And then we also take the logarithm of that distance, and we take the cosine of the turning angle. And the reason is why we take these parameters is that for the step length distribution, that can be characterized if it's a gamma distribution with the step length and the log of the step length, and here this turning angle distribution that corresponds to a von Mises turning angle distribution. I don't go into the details here, but the reason is why we take these parameters and why we also make our proposal distribution so the distribution from which we draw the alternative steps from gamma and von Mises distribution is because then we can estimate the parameters of this movement kernel fairly easily. You're okay with this movement kernel already? I'd be a bit surprised, but maybe we can go a bit further and then perhaps it'll clarify a bit. So this is now one way of trying to visualize what happens, so how this movement kernel and the selection part interact. What we see here, and this is from one of the nice papers on movement that's also in the folder. I come back to 6 main papers at the very end. This is one of them that I've found really nice. So what we have here is, this is for simulated data, a landscape. It's always the same landscape of selection. Yeah. So this is the white stuff is good and the black stuff is bad. Okay. And what is different among these 4 panels is how strongly the animal selects for the white or the black. Here it doesn't care about white or black. So we only see the movement kernel there, the part, the fly part. And then we have increasing selection. Now what do we see within one of these panels? What you see inside here, these are lines of equal probability of that the animal goes there. This is like elevation lines. Yeah? So the animal is here, and it's most probable that it stays here, and then it goes out further. And then it's more likely that it's here than here. And these points have equal probability. Yeah? And when there's no selection, then the gray level doesn't matter. It's only a question of how far away I am from where I am now. And now, here the animal has a tendency, but a mild tendency, to go to the white spots. And so suddenly things get a bit distorted. And this part here is being selected, although it is pretty far away. Yeah, so this has a higher probability of being there than certain other areas. Or in here, there's a higher probability to be there than there, just because that is selected. And if the animal is really, really keen on being in the white part, then it would not be found here, essentially. Even though this is close, it would always go up to there. And here it's even more extreme, that here, once it's here, the next time step you won't find it here. If it goes in this direction, it'll always be somewhere in this area. So this is to illustrate a bit how there are 2 parts that determine where we can expect to find the animals in, say, 3 hours. One part is just a question of distance from where I'm now, and potentially the direction, if we consider several steps. And the other part is related to the underlying habitat. I have 2 slides here for the integration. I think I'll skip this now and show you an example of what we can do with step selection functions. And then, if we feel like it, we can come back to this later. Okay? Now, this is an example that I always like to show, which is a very early one. I mean, this was 2011. Where they were interested in jaguar movement in Mexico. And one of the questions was whether along this highway here, where they should construct a jaguar path over the motorway. So jaguars were captured in these 3 sites. We have some protected areas here in darker colors. There are other roads here, and then we also have some areas where people live. And the first part, in a way, of this analysis was, well, what kind of habitat do the animals select? And they made separate models for males and females. And they tended to move into areas with high NDVI, so they would rather go to greener areas. They they would tend to avoid roads, and the females would more strongly avoid them than males. Yeah? So they really would avoid being close to a road. And then the last part would be that human population density, the female would strongly avoid areas with high human population density, whereas the male wouldn't really care so much. Yes? Sorry.
I just wanted to clarify, did they do this using a resource selection function?
This was
first?
step selection function
Step
type.
selection, okay.
Yeah, and we'll see in a minute why it was important that it was a step selection.
Okay, perfect. Thanks.
Did I say resource selection?
No.
Well, anyway, so I mean, if we had done a resource selection function this way, then we would have afterwards a map where the animals are and where they are not. But it doesn't tell us where they cross a road. And what they did with this model, once they had fitted the model, they could do something like this. Sort of you simulate with this model. So you have your virtual animal, virtual jaguar that runs around in the landscape. And you let it run around for a long time. And then the first thing you get out of this is something that you could have gotten also with an RSF that tells you how often do you find females in a certain area. And there you see that they're clustered away from human populations. And here you do the same thing with male, and you see that they are more or less everywhere. Yeah? Which makes sense because they have less strong avoidance behavior of human population and of roads. But when you now run this thing, you can also ask yourself, well, across this road, since I have a trajectory, where do they cross? Yeah? So you do thousands and thousands of steps, and then you make an analysis later on, where did the animal cross the road? And that's what we see here. So this is this section that was studied up there. And you see a histogram of how many times a male or a female simulated jaguar crossed the road. And you see that for the males, there isn't really a pattern. But for the female, there is this section here in the road where they tend to cross. And then I translated that to this point here. Oh, that's the point here, and that's where the bridge was built. And I think for me this is a nice example where you use the power of a step selection function, the capacity of it to produce trajectories that you can then later analyze these trajectories to say, well, where would these virtual animals cross the road? So what I want to do with you now is to go a bit into the pros and cons of this approach and then illustrate some with sort of Scylla-derived step selection functions, what these pros and cons are, before we then go into the concrete example. Yeah. So what is nice about the SSF? Well, it estimates the effect of the environment. RSF does the same, but they do this. And this is now something that I consider a real strength, that you can generate from this model new trajectories to, in a way, use this already for understanding whether the model does something that you consider reasonable. Because when the simulated animal produces tracks that you immediately say are completely unrealistic, that means that your model does not yet capture key elements of what you think is part of the ecology of your species. We'll see this in a minute, how that works out. And what is also nice about SSF that you can do this with very standard software. We will be using the package AMT to help things, but under the hood it uses just standard conditional logistic regression. And the Poisson GLMM is there for mixed effect models, so if you have multiple individuals, you can do that as well. As main drawbacks is that you have this single fixed time scale, although there's now some methods to get around that a bit. And you still have this beaming of individuals, so it's not easy to take into account what happens between these 2 points during this, say, 3 hours time interval. Another set of drawbacks is that you're not free in choosing the time scale. So you can't often use the most fine scale data that you have, because there the velocities are not yet autocorrelated, not yet uncorrelated. And the parameters that you estimate are to some extent dependent on the time scale that you choose, whether you use 3, 4, or 5 hours intervals, for example. That's very obvious for the time step distribution, right? The longer you wait, typically time step distributions will be, the average time step will be longer. One thing also that you cannot do is integrate hidden states, at least not in the. So if you say we discussed this about segmentation, Ili was talking about that a lot. So either the animal is foraging or now it's running around, then it will have different ways of moving, different ways of selecting, that you cannot easily take into account. What you can take into account is observed states. So if you know the animal is, I earlier used, it has a high temperature at that moment, or you have other ways of knowing what the animal is in which state, then you can use that information. But you have to attribute to each step what state it was in. Then you can use it. And to get to the range distributions in general, this is costly because you have to do a lot of simulations. But some of the things that is really nice is that you can incorporate quite some ecological realism, and I want to show some examples of this. This one is from the same paper I mentioned earlier, Forrester. You can make the selection of certain habitats depend on time of day. So here they looked at, for some elk, whether they preferred or not certain habitats. And you see that the burnt forest was selected for in the morning, but not during night, for example. Yeah? So this is, and the same happens, here it's not very strong. You can have also your step length be a function of time. So you say the animal moves a lot in the morning and in the evening, but not a lot during the day and during the night. That's something that you often see. And I'll show you how to do this, which accommodates already a little bit the variation in behavior over time, but not in terms of state. Now I'm active, now I'm not active, but just as a function of time of day, which could be a proxy of the state that the animal might be in. Then here, what comes now a series of images where we have Scylla in black, and then I fitted a step selection model to Scylla and iterated it, sort of generated a trajectory in red. And in this first model, I used the distance to water as the environmental variable, which is slightly different from what we had seen so far, but here's the river, so I used the distance to the river as an explanative variable. And I think this came out significant. and when you look at this, well, then you have a model, it's something is significant, but does that well describe what is happening? And you don't see it when you look at the model coefficient, but you see it with a simulation. So what works and what doesn't work? Could you tell apart which one was the real Scylla if I just gave you the two trajectories? Yeah, so what are some of the things that are weird?
Well, it crosses the river, which real Scylla never did, and it doesn't seem to mind elevation quite so much, which real Scylla did seem to mind elevation and slope quite a bit.
Yeah. So those are already two important aspects. So there's, yes?
Real Scylla is also much more tortuous. Seems to be returning and home ranging, like returning to a central point much more often, whilst the simulated one has much longer, more direct movements.
Yeah.
And is less concentrated.
Yeah. So it doesn't have this. It doesn't really come back. I mean, it comes a bit back because it likes this, but it doesn't have this tendency. So yes, let's look at what happens when we include this tendency to come back to a home range center. And then you get this. This looks already quite a bit better, I think. But you still have what you said earlier. It's still crossing the river. Yeah? So you can then add a new layer in the model. That's the layer that we see here to the left. I'm on this side of the river or I'm that side of the river. This is just a binary layer in my statistical model. And although there is this point here, which in the data we're not using it because it's a wrong point. And when you then fit it, there's a parameter that tells you it's not crossing the river. Yeah? Chris said earlier this would be infinitely high because that would be the maximum likelihood estimator. In practice, with the tool we use, it'll be a finite parameter, but it acts almost as saying it's never crossing. Yeah, and then and this is now something where you can bit by bit adapt your model, and you can judge the quality or the improvement not only by AIC or whether your parameter estimates are significant, but you can also judge it by its capacity to produce tracks that are a bit more realistic. Now, this is an informal way of judging the model, but I think it's quite useful. I then mentioned earlier that we can also deal with situations where you have long-term directional movement here. This is Leo, the vulture, with its winter and summer range and going back and forth. And now the question is, can we simulate or analyze something like this in a step selection model framework? And I tried now with different explanatory variables that I calculated. And here are 3 of them. The first one is just saying it's land or not land. The second one here was that I included the distance to the breeding site. And I set area over the water to you don't go there. Not at all, never, ever. And then here I said, well, you can go over water, but it's just much, much more costly. So it costs you 100 times more or 1,000 times more than going over land. And once I assign to each pixel in the landscape a cost, depending on whether it's on land, then it was cost 1, on water cost 100 or 1,000. And then I can calculate from each point in the landscape the cost, the cumulative cost to get to the site where I want to go. Okay? And then I use this layer as explanatory variable. And these are then simulations by using different types of variables in the model. So here we see in red, when I only take as explanatory variable the distance to the breeding site, then it goes straight there, which is quite a bit different from what Liu actually does. But if I now have this cumulative cost to the breeding site, the simulated animal for a long time follows very closely the observed animal, and then somehow here it's doing the straight line, whereas Leo deviates always a bit to the east. And this could be now something to think about. Why is it doing that? Are there dominant winds that would make that she goes there or not? So we can now think about potentially additional variables that explain this. But the main thing here is to say, well, yes, it's possible to have long-term attractors in a step selection function, even though we model each step new. There can be something that attracts the animal in the long run. So we touched upon this before, that when you do these models, you have to think about the context of the particular analysis you're in, and that the answer you get depend also on what setting the animal was in at that time. So if you have an animal that is in an area where a certain resource is very scarce, it might have a different response to it than when it's a resource that is very abundant. And the same thing is that the behavior of an animal might be different when the population density is low or high. For example, the home range will typically be smaller when the population density is high. So in a case where the population density is high, the animal will have a much stronger tendency to come back to where it came from. So this is just there to remind us, although we focus here on the technique of doing a particular model, we always have to take a step back once we've done the analysis and reflect on, well, what is it telling us here, and what could be reasons to really question or caution the particular outcomes that we get here from our analysis. So this is the last slide before we can go into the examples. This is just 6 papers that I think are really worthwhile having a look at. Here to the left, these are the 2 papers for RSF. I mean, this is the one that I said earlier is really about species distribution modeling. But when I read it at the time, I found it really enlightening. And this is 2015. I mean, for me, this is yesterday. And it took us as a community a very long time to get to that point here. And then this is more recent. This is Jesse's paper on the RSF. And then here we have perhaps one of the key papers in step selection functions. And this is an earlier one that I think contains a lot of good ideas as well. And then down here are papers that are a bit more about interpreting things and thinking about the concept. So this one here by Gerd Arzt and others is talking about this use availability framework and going from geographic space to environmental space and coming back. So I found that very useful at the time. And this is more looking at how do we interpret the parameters that we get out of our analysis. They're both by John, so there's a similar perspective there. They are all in the recommended reading. You're a bit tired here. Do you have questions now, or should we go straight to the R code?
Is that a question?
Hmm?
Is that a question?
Yes. R code? Perhaps that gives us some concrete things to bite into. So, what for that? Well, this is really small. We are going to work now with the SSF AMT 2024.R, and we are going to use in our working directory the Scylla fit RDS to speed things up, but if you don't have it there, it's not a big problem. The main thing is, for this to work, you need the GitHub version of AMT.
Just one question. Does everybody know how to install from GitHub?
Does it?
I just wanted to ask, does the step selection function work when you have gaps in your data, such as missing nighttime data, or if you want to look at a very specific behavior?
We'll see this in a minute. So you always, in general, the method expects that you have at least 3 consecutive locations or localizations or GPS points at the time scale that you're interested in. It's no problem if then you don't have observations during the night. So you have during the day you have observation every hour, and then you don't have for 12 hours, and then for 12 hours you don't have them. That's in principle no problem. But you then have to context. Be aware that that your analysis is an analysis for what the animal does during the day. And that then potentially when you create a simulation from this behavior, that this will look different just because you exclude the nighttime behavior, which might involve the animal always coming back to the same point or so. But in principle, it's not a problem to have gaps. It's quite a bit inconvenient if it's very irregular. Although, as I mentioned, there are two papers that try to alleviate that. But sort of the traditional response until earlier this year would have been, it's a big issue. And this is also what we'll do here. We'll work with one time scale. And I guess I was fortunate enough in my practice to work with animals where this was more or less so far the case. I think with the black grouse, this will be a bit different. So I'll have more experience with dealing with these methods in a short while. But we'll come back to this thing with gaps, the data and how to treat them. This will be one of the lines we cover. So here's a bunch of, you're good to go? So this is a bunch of packages that we work with. I perhaps want to highlight this one, which is the package that we need if we want to have the selection a function of day or a function of year or so. This is something that allows us to have something that is periodic in time. Yeah? And the rest is perhaps not so super interesting. And then the main package we're going to use here is AMT, which is written by Johannes Siegner. And that has, I think, done a great service for us as a community to be able to use these tools in a streamlined and well-maintained way. So we start with Buffalo. We now, as always, have to translate data from one format to another. And so far, it's not yet integrated in AMT, though this will happen soonish, I guess. And thanks to Anna, we have here a function that allows us to do the translation. And then we just apply this, and we have now an object called Buffalo tracks, which is in the data format that AMT uses. Next, we load again the Buffalo the environmental data, and we here translate again from raster to a Terra object. And then we always want to start with the summary statistics a bit. And then the Buffalo tracks, they have just, in this case, 4 columns, an X column for the X coordinate, the Y coordinate, time, and then ID. And you see that there's always this trailing underscore, and that is what Johannes systematically uses, that there are sort of specific names for specific columns in the data set, and we can use that then later on in our model formulations and so on. So we always know that X underscore is the X coordinate, Y underscore is the Y coordinate, etc. This will get slightly more complicated with the steps, but this is the general idea is specific columns have always a specific name. So we've seen this now a few times. This is all the data. Now here we focus only on Scylla. And now we will start with looking at this movement part of Scylla. So what are the step lengths, etc. So when we look at the histogram of step length, we see that this is, most of them are way less than 2 kilometers. And then there are some that seem to be very high. And when we look at this, there's one step that is more than 5,000 meters. And this happens to be the first step, and that's why I strongly believe that there is something weird there. And here we just overlay data for the first day. And it seems that here's something really weird happening. And so perhaps this was, they switched on the GPS or whatever, then they drove there. Or I don't know what happened. But I suggest that we just throw this out. Yeah. So, and now comes the step in SSF that we, at least for now, have to do. We have to thin the data to our time interval that we want to work with. Yeah? Yes.
Are you throwing away on the first day? Or
yes.
no?
I felt, well, what the heck? I mean, it could have been the question was whether we throw away the whole first day. I felt yes. I mean, we have enough data in a way, and I'm not particularly interested in the immediate response of the species, and I don't have enough information on this data set, whether this is really reliable information. So I'm not suggesting that you should always throw away the first day. It's just, here's something fishy. I have not a lot of additional information, so I felt, well, rather lose a bit of information than having some very weird data points in there. So when we here look at the summary of the sampling rate, so this is a function in AMT, it tells us that, well, most of the time points are separated by 1 hour. So this is true for at least the central 50% of data. When we look at the first and third quartile, also the mean is about an hour, but there are some where it's more than an hour, and then we have also some that are very close to each other. And but so we have data at 1 hour. Now, there's a bit of a debate. So I want the data to be thin to the point where the velocities are not autocorrelated any longer. Because this is an assumption of my model. And I know if I don't meet this assumption, then all sorts of weird things can happen in terms of the p-values that I get and perhaps other things. So that's why I thin here to the point where the autocorrelation in velocities has decayed sufficiently. Other people feel we should use all of the data. Yeah? I will teach you how to subsample. If you do it then differently, you do it differently. But I think it's better to go for 3 hours than to have something where I don't trust my model as much anymore because I've violated certain assumptions there. So then how do I know what timescale to work on? Well, CTMM can calculate this timescale for us. So that's why we first do here a telemetry, or we look at an variogram. Here I just focus on the initial part. And we see here that there is this curvature. Yeah? And as long as there's a curvature, then velocities are autocorrelated. So I mean, here already by eyeballing, the question is when do we get in this linear phase? This looks pretty good. So it's somewhere here. Yeah. Somewhere here is probably what we want to use as a step length, or as a time step. But we can do this a bit more formal by again plotting the variogram. And now I put here the times in vertical when the autocorrelation has decayed to a certain amount of, to a certain percentage. So the yellow one is when it has decayed to 5%, here to the red line to 2%, and the blue one to 1%. And so this suggests that if we go to 2 hours, we are borderline in terms of autocorrelation in velocities. So I would go for 3 hours, but 3 hours you should be a pretty safe bet. Where's the? I just keep it.
I don't think I quite understood that. So is it kind of more of like a visual inspection of this, or is there like, because when you run the models, sometimes they vary between like OU and OUF. And so is that trustworthy, or is it more of like this visual inspection?
So here, what I did is I first fit the best supported CTMM model by using CTMM select. And once I have this model, I have one parameter that tells me what's the autocorrelation timescale for velocity. And I take this value, which has been sort of, this is my best estimate for this velocity timescale. And from that, I can actually calculate how long I have to wait for the autocorrelation to decay to a certain level. Yeah, because the autocorrelation decays exponentially with a rate, and this rate is given by the time scale. So and sort of I can here sort of, because it's exponential, I put in here the logarithm, and in here you can put the p-value sort of, or the degree of autocorrelation that you want to accept. So say 5%, and then it will calculate me in hours. That's why I divide here by 3,600, because otherwise it's in seconds. The value. This is so it's the eyeballing I just did because I often feel this is quite nice and intuitive. And I feel also just by eyeballing this, we would have excluded at least these two as being still in the curvature, and probably this also being a bit borderline. And then the formal analysis provides us there with a nice indication. So I mean, I always like to have something that is calculated, but have sort of an intuitive backup. So that's why I started with this visualization, but then we can calculate it and have a sort of as a rule, I want to thin down to 5% autocorrelation in velocities. And I put in several ones here so that you have a bit of an idea of, I mean, here there's not much choice because they all fall more or less in the same point. So So it's around, yeah, around 3 hours. That should be good. So now we set this as just as a, yeah. Coming.
Thank you. What are we then getting in the summary output for the fit, the model that we fit using CTMM? Because you know how we get an estimate for the velocity there?
Yes. So I mean, if you look at summary fit, huh? So you get here tau velocity in 44 minutes. And here I pull this out specifically here. And this value here is in seconds. I think if I don't divide this by 60, that's 42. I don't know why they don't exact. No, that's the high. So here, so they match exactly. So, so I take this estimate out of the fit object, and I know this is in seconds, and then on this plot I want it in hours. That's why I divide here by 3,600. This is a bit. You have to look at what units am I in, and but the time scale, velocity time scale, is from the fit object. Yeah, I glossed that over a bit. Yeah, but it's, we use in this whole code. I use CTMM only once, and I only use it to get an estimate of the time scale that I can best use for the SSF, because I know that the velocity autocorrelation has to decay. So for that, I need to have an estimate of this time scale. I get that from CTMM, and then I say, well, because the raw value, if you wish, is this 42 minutes. But now, and we said when it's twice that, then it's roughly decay to 5%. So that would be a little less than 2 hours. And here, yeah, so it's, I don't know why I I arrive at a little more than 2 hours for the 5%. So, but it's always coming back to saying CTMM gives us a good estimate of some basic properties of the movement characteristics of this animal, and we use these then in our statistical analyses to match the assumptions that are inherent in the methods. And here, so far, there is no funky downweighting, so we just throw away the other information. I make a comment further down how one could use all information, but the traditional way is now we thin to 3 hours. And this thinning to a certain time step is what can be done with trajectory samples. So you put in the original track, you say to which target step duration you want to thin, and you can give it a bit of a tolerance, saying, well, if it's not exactly 3 hours, but 3 hours, 10 minutes, that's fine as well. And then it tries to find the best subset of points that is in line with this requirement.
Is that tolerance both positive and negative? So
Yes.
like before or after? Okay.
Yeah.
Sorry, the tolerance. So if I have one exactly at 3 after 3 hours, and for some reason then I have another GPS point at 3 hours 10, we'll always take the one that is the closest to the 3 hours, or we'll take them both?
No, it will only.
No,
I mean, it will make sure that
needs
in
to
the
take
end
one,
they
yeah.
are at points at least 2 hours 45 minutes apart.
Yeah.
I think it is pretty smart, so that if there are 2 points, it'll check, well, what's coming afterwards. Which one do I drop so that I keep as many as possible?
Okay.
Yeah.
Thank you.
But I'm not 100% sure. So when we now look at the sampling rate of our thin data, we see that they are at 2 hours, almost 3 hours is the shortest one, and the max is 4 hours. But what has happened now is it has created us some bursts. A burst is something where, within a burst, everything is only 3 hours apart. And if then there's a gap of more than 3 hours and 15 minutes, it'll start with a new, what is called burst. Yeah? And the length of this gap can be very variable. And then it starts and then continues. So we have here two bursts. So there are at least 2 points that are further apart than 2 hours. But this is, in principle, there's absolutely no problem. And the only thing that is problematic is if the number of observations within a burst is too small. We need at least 2, because we need at least a start and an end. But we typically like to have one initial point more, so that we can calculate turning angles. To calculate a turning angle from here to there, I need my time not only now and future, but once back. So that's what we do here. We filter those bursts that have at least 3 observations. And we can look at Scylla now here. So this is still very much a location for a given time. The idea of the animal, and then which burst I'm in. For our steps, selection and
just to understand because we are selecting like the tolerance, we are using 3 hours and the tolerance is 15 minutes, but why the max is 4 hours? Is it because of this burst? Because in the table, the summary, the max is 4 hours.
Yeah. That's so the end point of the first burst and the initial point of the second burst, they are these 4 hours apart.
Okay.
Exactly.
Thank you.
And how did you interpret the summary table to know there were at least 2 points greater than 3 hours and 15 minutes?
2 observations. I mean,
2 to create the single gap.
Yes. Yeah, there's one gap, but yeah.
Okay, I think I understand.
Yeah. So this is There's at least one case where the second observation is more than 3 hours apart from the first. So that's why I call them 2 observations, because this gap between these 2 is more than 3 hours. But it's only one gap. Chris?
At some point, it might be worth mentioning, a number of people have realized that you can, if you pick a very specific movement kernel, which is the one for, say, for Brownian motion, then there's a nice little trick you can do to help with a little bit of the irregularity in the sampling.
Yeah.
I don't know if you're going to cover that or not.
I mentioned that there are two papers that deal with these things, and one of them is the one that uses a particular step length distribution to deal with this. That's the one you mentioned there. And then there's a second one that also deals with this, and they're both in the. I think I put both of them in the recommended reading. And they are mentioned, sort of the titles are mentioned earlier in the slides, which you have. I haven't in practice used that yet, so I'm not covering it in practice, but that could be a nice exercise to do.
The one that's I think the Rayleigh distribution,
Yes.
It's very simple. You just divide the step length by the square root of the time lag. That's all you have to do. You're done.
No, I mean, technically, I think it's not difficult to put in practice, but I haven't tried it. I haven't really thought about this, so that's why I said, well, yeah, it's cool. It's out there now, but that's why I didn't go into this any more than that.
Chris, and you said that helps you deal with data sets that have like little gaps and irregularities?
Yes, if they're not, the points don't exactly come in on the 3-hour schedule. If some of them are a little longer and some of them are a little shorter, that corrects the movement kernel part, but it's not a complete correction. It's like a half correction.
So, I would like us to get to the point where we have fitted our first SSF. Yeah, so that's where we want to go now before the break. Yeah, So now we have a location data set there, and for the step selection function, we need steps. So what is a step? An initial location and then the follow-up location. And there's this function step by burst that will create that for us. So let's have a look at how this new thing looks like. So now each line is a step. A step is something that has an initial coordinate and an end coordinate, and it has a step length, and it has a direction relative to north angle, and it typically, if there's a prior step, you have a turning angle. You don't have it for the first step because. So this is what a step data frame looks like. Clearly, there are some observations that don't have a turning angle, and there are 2 of them. You have at least 1 per burst, because in each burst, the first step doesn't have a prior angle. So we now throw them out. And again, it's worth looking at these other papers we were just discussing about that provide ideas for how to deal with irregular sampling schedules, because that here we are throwing away data, and you might not have to throw away all of that now with these new ideas. And for Scylla, it's not so relevant because we're not throwing away a lot, but if you have highly irregularly sampled data, then that can become easily an issue. So now that we have our steps, we can have a look at the step length and the turning angles. So this is how this looks like. Here to the left, the step length, and here the turning angles. And this is, looks pretty much like a rather exponential distribution. And then here for the turning angles, we see a fairly clear patterns. What would this pattern suggest? There's directional movement, right? I mean, this is when the animal moves in the same direction. Next step, and there's a strong concentration around this. So I said earlier that what we typically do in an SSF, that we propose alternative steps according to the observed movement kernel. And in order to do that, we will now fit distributions to this so that we can then draw alternative steps from this distribution. So from the distribution of step length and turning angles. And those are used then to generate our possible alternative steps. And here I first want to show for the step length distribution, there are two. There's an exponential and a gamma. And we see in this case they look extremely similar, the two of them. I mean, the gamma is a generalization of the exponential. And in this case, we might, in a way, you could argue we don't necessarily need this flexibility. But it doesn't hurt us in our process. So I would typically use the gamma distribution for the step length distribution. And then for the turn angles, here we see the observed ones, and then this is what we propose, what we will propose. And the function to create these alternative steps is called random steps, and we give it our original object with the steps of Scylla, and we tell it how many alternative steps we want to have created. And I feel that 200 seems like a good minimum number.
Bjorn, I have a quick question.
Yes, yeah, that was just, yeah, sure.
Yeah, I just wanted to verify. So 200 per step, so that's like 200 alternative options to compare against? Oh, that's a lot.
That's a lot. Yeah, if you have 1,000 steps, you end up with having 200,000 points. Yes.
Sweet. Thanks. Just wanted to make sure that was...
Yeah, but I mean, in a way, what we want to do there is we want to represent all options that are there. So we have to approximate this integral, and for that we need quite a number of points. I think. I mean, what you could do is you could, and that is what is done in RSF fit. If you use not the Riemann option but the alternative option, RSF fit has a criterion to check whether you have already enough points to well approximate the integral. And this one could implement that also for SSF. So far, nobody has done this. So that's why we kind of always have a bit. So the idea is you need as many points so that your overall likelihood or log likelihood doesn't change anymore as you increase the number of steps. As long as that, because that will fluctuate. Your log likelihood will fluctuate as a function of the...
Martina's saying goodbye. She's attending a friend's wedding.
Have fun.
So you don't want your likelihood, which you then use to do model selection, all sorts of things. You don't want that to be dependent on the random number you want that to be a fixed, more or less fixed number. So you could essentially check. You do this analysis. You change the seed. You rerun the analysis. You check how much your likelihood changes, and then if that is still changing by something that is noticeable, you increase the number of steps because eventually it won't change anymore. And that's then the point where you can say, okay, now I'm good. I mean, this is the broad idea, and then you could look up how Chris is doing it in RSF to mimic this. But my feeling is if you're using 200, you're doing more than almost anyone else. So for now, and I think as long as you analyze the data for one individual, that I don't think this is typically a problem. I think this can become a problem when we are talking analyses for multiple individuals at the same time. So then we have to rediscuss. But if it's possible, use that. I mean, there's another paper that I did not put in the. First, the effect or the fact that you might need a lot of background points to do an RSF, that was already in the Renner paper, and I remember when I read this, I was quite surprised because in the species distribution modeling literature, we used to take 10,000 background points. And we thought 10,000 that's a lot. And compared to 200, that's quite a bit more. I mean, here you would multiply the 200 then with lots of steps. But still, 10,000 was sort of the norm. And they do this analysis on how the likelihood varies as a function of the number of background points. And they go up to 200,000 for it to stabilize. And I think that's something that in RSF also can happen quite easily, that you have hundreds of thousands of points that you need for the likelihood to be not very much affected by the particular sample that you have.
So these 200 are being created just randomly around each of our points that we already have selected that are spaced out. But we haven't provided any information for these 200 steps, how far they should go.
We do. It's not explicitly, but internally what it's doing with random steps, it is looking at the step length distribution, and turning angle distribution of this object.
So it is already taking in consideration the space out.
That's what it's doing.
Okay.
Very, very good point. So that's just a default argument that it's doing this. I show in the code for the analysis of multiple animals how you can make this more explicit.
Okay.
Yeah, but very good point.
No, it was the same question.
Here, so it's too small. When you look at the helpful random steps, then you see that there are two objects there. The distribution for the step length and turning angle that you want the function to use, and that by default it is taking a distribution here. It is taking the distribution from this actual step length and actual turning angles in your data and fitting a gamma distribution to the step length and a von Mises distribution to the turning angles.
And so what point does it filter out unrealistic steps? So if it ends up stepping into the ocean, is that within this, or is this
that comes later?
Okay.
Because here, at this point, we haven't seen the environment yet. So there is one of the next steps will be to extract environmental information. And at that point, you can say, no, I don't want this, I don't want that.
Then you still end up with exactly 200.
No, then you have fewer. And that's not nice.
You can't go back and resample.
Yeah. But I mean, in theory, you could do with fewer, but then you would have to give them a higher weight so that. Yeah, there's still a lot, say, things to consider yourself. I think we skipped this. This is just a plot thing. Now, we can have a look at SSF Scylla here. So that's always a good thing once you have changed something to look what happened. And what is now new is we have here a column case underscore, and case is 1 for the real step and 0 for an artificial step. And then there's step ID, and that groups always together the real step with the 200 alternative steps. Yeah? They form one package. That's one step ID. And then for another step, we have another 201 observations, and they get their another step ID. And then later we need a statistical model that takes this into account and always calculates the integral, sort of sums up our background steps for exactly this particular step. Yeah? That's why we do a conditional logistic regression and not a classic logistic one. So we stop some plotting, and then here we now extract our covariates. And so we need only 2 arguments, which is our steps and our environment. I recommend that you use the option both, and I explain why. So let's first do this, and then have a look at head of SSF Scylla. So we now get the same thing as before, but we get additional columns, and now for each layer in our Buffalo stack, environmental stack, we get, for example, elevation. We get elevation start, and we get elevation end. And that means, because for each step we have where we started and where we ended. And we now get the environmental conditions at the start and at the end. And this will later allow us to not only model the selection, so that the animal goes to the environmental condition at the end of the step, but that there can be also an impact of the local environmental conditions on my movement behavior. So it could be that if I'm in a forest, then my step length will tend to be shorter than when I'm in open land. And for that, to say that the current environmental conditions influence how much I move, for that you need the starting environmental conditions and not the end ones. The ends are for being attracted or repelled, and the local ones are for moving faster or slower. Yeah?
Sorry, I don't know if the others are experiencing as well. I only have always one less than you as new variables. 14 and before was 4.
Perhaps you get one more column here because you're.
And then it's just, that's why
you
it's
might
not
get
hidden.
T1 on as well.
Okay, thank you.
The point you just made about the starting and the ending variables, does this mean that in the model we'll have separate coefficients for each covariate, one for the start and one for the end?
That depends on what you put in your model. The traditional version of the step selection function would be you have only the endpoint conditions and say that's my selection. And you wouldn't have anything for the start points. The start points, and that is, I mean, I think the first paper where I saw this, that you could do this, was the paper by Talafgar, 2016. They said, well, my movement kernel, sort of step length and turning angle, they could actually be a function of environmental conditions. So that was, for me, a really neat idea. And if you want to do that, so if you want to have your step length or your turning angles be a function of environmental conditions, then you put in the start. So they come always in as an interaction with turning angle or as an interaction with step length.
Okay.
So, and I find that is quite often quite an interesting thing. So when we looked into our frogs in the ski resorts, they were not really selecting the endpoint very much between these different grassland types. Yeah, they were selecting for being in more humid areas, but in terms of these two, they weren't. But they moved at different speeds in these two habitats. And then we interpreted this as being, well, it's moving very fast in one habitat that is a dangerous habitat, while it's also easier to move in. It's the specific interpretation you have to then see, but because it's more open, very, very short grass, they were moving faster in that than in more dense grass. But it's not that they did. If you gave them a choice, it's not that they would go into this or that. But once they're in there, they move faster here than there. And I think that's really a nice part of this tool that you can bring in these biologically, I mean, for us, immediately intuitive elements in these models. So I feel in certain respect they're very nice and flexible. But you have to be you have to be careful that if you want to integrate the effect of environmental conditions on the movement, then you have to do the both and have to use start. Otherwise, you do weird stuff. Yeah? Because then you start to try to say I'm moving differently now because I might end up there or there. That's not so obvious that this makes sense. So I recommend you always use both and then have in mind selection is where I move to, so that's the end, and changing in my movement behavior, I approximate that with the environmental conditions where I'm now. We're almost there. Now, I said earlier that we can make our movement behavior, both in terms of what we select and in terms of how far we move in a given step, a function of time of day. And in order to do that, we need a variable representing time of day. And this is one way to create it. So this would be then called hour. So this would be the time of day in hour. Oops. How come? Did you get that as well?
No.
Interesting. What happens if I ignore it? But it's there. Well, we don't need it for our first model, so we ignore it. Did I run this? I did. Uh-oh. Ah, you know what? This is just, this part here is RStudio being weird. So that's not problematic. It's just that I guess I should start here again. Yeah. So this we just ignore this. This is. So then we remove NAs. So this can happen. This was a question earlier. What happens with NAs in the environment? We could also there remove things that we don't want it to go to. But I mean, if it you could chuck in just ocean as an explanatory variable, as a habitat type, and then you would learn that it doesn't go there. Yeah, because sometimes it might go there, though this could be just due to GPS errors. So that is always a bit of a question. Do I use something where it's not supposed to go as something that I actually fit, or I throw it out completely? Yes.
Is there ever a scenario where you have your 200 steps, and when you merge it with the environmental raster layer, these steps are actually falling outside of the raster, and then you get NAs?
Yeah, that happens.
So then at this step, you would have to be careful that you're not losing, or does it not matter if you lose 1 or 2 out of the 200?
I think if it's 1 or 2, it's not such a big deal. If it shouldn't be a substantial fraction, and yeah.
Is there any way beforehand that so could we potentially do this step and then see what the extent is when we simulate all the points and use that to guide the extent of the rasters we then need?
Yeah, I mean, this is, you got there a bunch of x and y coordinates,
yeah.
So you can just plot it and then see is this big enough. I mean, here, we extract it from the whole Buffalo environment, so which is really huge. So I think there the problem is rather that I think there are just a few, that in the raster layer itself, in one of the raster layers, there are NAs. So that's why it's here, it's very rare. It can become more frequent. And the issue is later on also what happens when you simulate, when you do these simulated trajectories and you don't have a home ranging factor in it, then it'll eventually want to leave, and then Johannes put in an argument, so how many NA points you're willing to accept, and if there are too many, then it'll stop the simulation there. So now that we have everything together, we can do our first SSF. So what do we need? We use the function fit_clogit, which is in the AMT package, and it's just a wrapper around the function clogit, so which is a conditional logistic regression, but it does some nice things for us. It stores, for example, our proposal distribution, so the step length distribution and the angle distribution, turning angle distribution that we use to create our alternative steps. And then we give it a formula, which is, you can stick in here what you used from R as in terms of formulas. So you can have, here, for example, you don't have to create a variable, the cosine of turning angle. You just say cosine of turning angle here, and R will know what to do. Same with the logarithm of the step length. And here you can have interaction, you can have polynomials, you name it. Huh? And then the one thing that we have to do in a conditional logistic model is you have to tell it what they call strata. So what is always a package of a realized step and alternative step that belong together. Yeah? So, and that is the variable step ID underscore that was created earlier when we did the steps by burst.
So speaking of burst, is it fitting separate models for each burst? So how is burst taken into account in this?
Here, not at all anymore. So the burst was only there to avoid that we suddenly have very long steps because the time step between them is too long.
So it was used to create the steps, but then no longer.
Yes. And this is, I mean, this is one of the things that at least one of the two papers with the irregular step lengths try to address. What do you do when you have just not a gap of 10 hours, but a gap that is just one observation was lost, yeah? Which can happen with GPS failure. So, and then if you use this approach that I propose here, you potentially lose a lot of steps, because whenever one point is dropped, then you start a new burst. And when you start a new burst, you lose one observation because you don't have the turning angle. And then they said, well, can't we do something? And they came up with ideas of what you could do. Okay. Yeah, but yeah, that's a very nice point. We do this whole burst thingy because we would get a problem with these very long time steps. Because then we would, in a way, you have to have a different proposal distribution, because you have to know, now I'm doing something for 6-hour steps, and that's different from what I need to do for 3-hour steps. Yeah. And that's also then the idea, in a way, to solve it, that you say, okay, well, let's do just different things for different step lengths, or different step durations, and that helps a lot. Yeah.
Great.
Did I not fit it? Oh. Now that we fit this, and we look at the summary, so let's start again, as we did earlier, with the environmental layers. So the stuff here, we have a bit more. We have slope, elevation, the mean NDVI, and the variance of the NDVI. And finally, something significant. Yeah? So, and this is what we now see is elevation is significant and the coefficient is negative. So if we throw this very simple model at the data that the animal is either always going downhill or going uphill, then there's a tendency that the animal always goes downhill. Yeah? That doesn't mean that it's always going downhill. This means that in the context of this model, this is what the animal would on average do. Similarly, we get something for mean NDVI. Here it is a positive coefficient, so the animal would have a tendency to select a site if there are several given, the one with a higher NDVI.
So even though it had the information for the start and the end, it's just calculating for the end because it's considering the start for the calculation, but we just care about the end. correct?
We do here, this. I only put the end in the model. So when we look at what we put in the model, it's only the end.
Okay.
Because this would be the classic thing. You're only interested in selection. So do that move to this or to that. So that's why we put in the environmental condition at the end. One more thing. Here we now have our 3 parameters for the model, for the movement kernel. And when you look at these coefficients, what do you see? I mean, in terms of significance and in terms of size. They're not at all significant, yeah. And also, they're very, very small. Well, whether something is small doesn't mean that it's not important, because we discussed that earlier. It depends on what the scale at which it is measured. But what is important here, that this is not a measure of the step length of the animal. What this is a measure to what the step length that we observe in this data, when we include the environmental conditions, is different from the proposal distribution. Okay, so we have a certain step length that we throw at it, from which we draw our proposals, and this is now how much it differs from this proposal. Yeah, so if you're interested, and I'll show you later how to calculate this, if you're interested in the actual distribution of turning angle, step length, and logarithm of step length, we have to make a fusion. We have to add the change to the original parameters. And with that, we then have our movement model. Okay? That's something that is important to keep in mind, that these here, it's not surprising that they're very close to 0, because all that it's saying is that the proposed steps were fine in terms of distances and turning angles relative to what we see once we correct for this. Yes.
Why is there no intercept for the model output?
That's a good question. Does anyone have an answer? Why is there no intercept?
Is it because it's kind of remodeling it? I don't know, but is it because it's remodeling maybe at every point? So it's almost each point will have its own unique intercept as it goes through?
In a way, yes. So what happens is we model this probability distribution. Yeah. So what we want is that, or what happens here in the model is that all the 201 points for a given step, the predicted probabilities, they sum up to 1. That's what the conditional logistic regression does. And because it always sums them up to a fixed number, we don't need an intercept. Because remember, we had we have the lambda in the denominator, and then we divide essentially by the sum of the other values. Now, if you had an intercept, then that would be in the numerator and the denominator, and it would just drop out anyway. So it would be thrown out anyway. So there is no, we don't have an additional free parameter here. That is then, I mean, it comes in, and then that's where your point is completely right. For when you can fit this model also with a Poisson regression, and then you have to have an intercept which varies. But that it is then chosen so that it integrates again to 1 for each step.
So for instance, if we were to include some demographic information, if we were doing this with multiple individuals, such as the sex, then what would be our, like if there's no intercept, how would you interpret?
So what you could have, if we stay now within an individual here, and you say you'd have it in 2 states. Yeah, you've whatever. How do you get 2 states for your animal? Somewhere you did a segmentation with 2 classes, and now you have for each observation you have, and then you wanted to say, well, say day and night. We do day and night, and we want to interact. We want to say, well, is it moving longer steps during the day than during the night? Then what you would do, you would put in here something like day-night, yeah, which would be a variable that is either 1 when it's a day or night when it's a 0. Okay? And that way then you would have 2 values for step length, one for the night and one for the day. And that's how you would get these effects. We will see this further down. So one thing that happens in SSF a lot, that we work with interactions. That something so you don't have I think you would have SL plus SL day night. So you'd have the 2. So then if this was 0 or 1, say if day was 1 and night was 0, imagine this, so this is one way to code it, then this would be how your step length changes relative to your proposal distribution during the night, and this would be how it changes then how the step length changes relative to the night during the day. And then if you calculate what happens ultimately what happens during day, you take your proposal distribution, you add what happens during the night, and then you add what happens during the day relative to the night.
Would you need another parameter for day-night?
Would you need another parameter just separately in? No, again, because that would be integrated out. So you often have, anything that is anything that is just a fixed thing would integrate out. I suggest we make a break now, and I think when we play around with this more and look at examples, and then we collect a bit these points which are a bit more technical, and then once we have more experience and more examples, potentially next week we then make a specific session to go into this, yeah, because that's